Alright, so now we have a block with mass 14.2 kilograms. Now it slides down an incline. Alright, I'm going to draw the incline like this. 37.7 degrees. And define my x and y axes as up the slope and away from the slope, like that. And so now I've got a mass that slides down the plane with a constant velocity. And then it's projected up the same slope with an initial speed of 4.70 meters per second. And it asks how far up the slope will it get to before it comes to rest. Okay, so drawing our forces on here. I'm just going to redraw everything. So we've got our mg, our normal force, and in the first part, our frictional force is going to be this way, as it's sliding down the slope, and then it's going to swap directions. But let's first do the first part. So we've got a frictional force going this way. And it says that our velocity is constant, so that means that our acceleration is 0. So now, first of all, let's decompose the mg force. So our mg force is here. That is going to be our 37.7 degrees. And then so then this guy is going to be mg sine 37.7, and this guy here is going to be mg cos 37.7. And if as my axes are xy, then this guy is x and this guy is y. So looking in the x hat direction, or actually, sorry, looking in the y-hat direction, we've got our normal force minus our mg cosine of 37.7 is equal to 0. So then our normal is mg cosine of 37.7 degrees. And now looking in the x direction, we've got minus mg sine 37.7 plus our frictional force. So the way I've drawn it, the frictional force is in the positive x direction, is equal to 0. So then our frictional force is mg sine 37.7 degrees, which is 14.2 kilograms times 9.8 meters per second squared times sine of 37.7 degrees, which is 85.1 newtons. Okay. So it turns out I didn't need to solve for the normal here because I could use that to solve for a coefficient of friction, but our frictional force is always going to be the same. Because our frictional force, well, it's not always going to be the same, but it's going to be mu n, and as long as our normal force doesn't change, then it will be the same. And because it's the same block being pushed up the same slope, we will have the same normal force. But just to confirm that, so our normal force here is mg cosine of 37.7 degrees. And now if we look at the case where the block is going up the slope, then frictional force acts downward, our mg is downward, and our normal force is this way. Again, going x, y, same axis. Our mg is going to decompose the same. So our mg is going to give us mg cos 37.7 here, and mg sine 37.7 here. So then if we look in the y-hat direction, we've got our normal force minus mg cosine of 37.7 is equal to 0. So then our normal force is mg cosine of 37.7 degrees. So our normal force is the same, so our frictional force is going to be identical. So now looking in the x-hat direction, we have minus our frictional force, because it's now in the minus direction, minus our mg sine 37.7 is equal to 0. But we already solved for both of these, so our friction was mg sine 37.7. So both of these are just 85.1 newtons. So then together, they're, what did I get, 100? Oh, whoops. So they don't equal 0 this time, sorry. They equal our acceleration. So they equal max. And so then our acceleration in the x direction is then minus, what is that, 170.2 over our mass, which is given as 14.2 kilograms. So then this equals minus 11.986 meters per second squared. Okay, so then there's our acceleration. So we're given our initial velocity is 4.70 meters per second. So this is in the x-hat direction. We're going to take our initial position as 0, and we're solving for our final position. So we've got xf is equal to xi plus vit plus 1/2 a t squared, where that's 0. We also, its maximum position is going to be where the velocity comes to 0. So we've also got that Vf is Vi plus At, where that is not 0, that's 0, sorry. So then our T is minus Vi over A. we can go ahead and plug this into our XF expression. Actually, it looks like I solved for it, so I'll just do that anyway. So it's minus 4.70 meters per second over minus 11.986 meters per second squared. So 0.392 seconds. And then plugging this into our XF expression, 4.70 meters per second, 0.392 seconds, plus 1/2 minus 11.986 meters per second squared, 0.392 seconds squared, and we get 1.8424 minus 0.9215. These are in meters. So 9209 meters. So that's how far up the slope we reach. Checking through our solution. You can compress all this obviously by subbing in the time, which is what they've done here. And they get a final distance of 0.92 meters. So that looks good.